this, how I'm going to, okay.
Cap.
The cap. You got the cap there. That's the cap. Okay, specific. That means per unit mass or per unit mole. That's the cap. If no, if it's a dot, if there is a dot on it, then it's the rate. So internal energy, as I mentioned yesterday, you don't have an absolute value. It's a state function. That means you cannot calculate it directly. You have to get a difference of internal energy. Okay? So how do you get the internal energy? You have to have a reference state. I mean, something to refer to. You have to refer to something and set it as zero. We will look at that later on. So what you're going to cover in chapter 8 is that equation. In chapter 9, you got not going to look at this, the integration part. But this integration, I just introduce it because because we introduce internal energy, so I just introduce this integration. So when you have no phase change, so this is the equation to calculate delta internal energy, the difference in internal energy, and you'll be using the specific heat at constant volume. Okay, that's constant volume. So next, any questions so far? Any question? Oops, I need to undo this. Oh, okay, enthalpy, again, you have come across it in thermodynamic. Again, enthalpy is not an absolute value. You have to have a delta enthalpy, delta H. Okay, you need to have delta H. Ouch, why is it being changed now? Delta H. And it could be a dot, there, or it could be specific, depending on the unit. So delta enthalpy is different between two conditions. It's not an absolute. You cannot get just enthalpy on its own. You just cannot get one value for enthalpy. There's no absolute value. You need to get the different. So how to get the different? Normally, you will calculate it using this integration. That will be covered in chapter 8. And this time, if you're calculating delta enthalpy, you'll be using the heat capacity at constant pressure. So again, there is no phase change. This integration is only valid when there is no phase change. And you need to take note of this, that when you are dealing with ideal gas, the function will be on in terms of temperature difference. This is very important because when you're looking at the integration, you will be integrating in terms of temperature. So your Cp will be in terms of temperature. Okay, so now let's go back to maybe if let's see whether I have this is one example inside your textbook. Specific enthalpy. Specific enthalpy. This is from appendix B8. I'm not sure whether your textbook is the same as B8 because my notes, some of them are from the earlier version, which is the third version. So if you look at this is specific enthalpy. So the unit is per unit mole. And you're looking at gases. This is specifically for gases. So at different temperatures, you will have different values of enthalpies. It is not going to be the same constant. It's not going to be constant at the different temperatures. So this is how you read your data of enthalpy. It's specific at one reference. So what is your reference? This is your reference. Let me delete this first. I'm talking. Okay, your reference is this. The reference is at 1 atm. This is at 1 atm. At 1 atm, and the temperature is 25. Why 25? Because at 25 degrees C, the enthalpy of these gases are all zero. That's the reference state. That means if you calculate your enthalpy, delta H, oh dear, it's quite difficult using this computer. So this is, let me see, trying, that's the cap, minus the reference enthalpy. Okay, that's your reference enthalpy. We will have a note to it. So your reference enthalpy, you set it to be 0. So when you set that to be 0, so whatever value you get, for example, at 100, that is the value for this, for that first value. So that is actually a difference. It's actually a difference between 0, between that value and 0. So that's what you get, 2.19. Yeah, the same thing if you do for delta U. Okay, any question? Any question, guys? Nobody asking? Are you with me? Am I speaking alone?
Yes, doctor, we are here. We are here.
Okay, okay. So this is what I was talking about just now. Delta U is equal to U. The internal energy is equal to the difference with the reference value. Your delta H, this is not inside the note because I just decided to put it today because I before this I didn't want to have, I did not put it there in the slide. So I just did it this morning. So you have to, every time you do an energy balance, you have to specify your reference state. You have to specify your reference state. Remember, when you do your material balance, what do you have to specify? I need some responses here.
The basis.
Yes, the basis. You need to specify the basis. You do the same thing here in energy balance. You still have to specify your basis, but you have an additional, you need to specify the reference state too. Okay, so this, your reference state is when you set it to be 0. So if you look at this table B5, which is the property of saturated steam, what is the reference state? Somebody? For your saturated steam table, what is the reference state for your internal energy? This is internal energy, and also for your enthalpy. Anybody? What is the reference state? You need to specify the reference temperature. What temperature?
0.01 Celsius.
Okay, 0.01 Celsius. What is the pressure?
1 atmosphere.
I don't know. You are looking at the table now.
Maybe.
0.0.
0.00611.
Okay,
Bar.
that's the pressure.
Oh,
And what's the phase?
saturated.
Gas phase.
What is the phase?
Saturated
Is it steam? Is it water?
Saturated steam.
Okay, somebody, who's the one speaking just now? Ibrahim? Is it?
Ayman.
Aiman. Okay, Aiman, you said saturated steam. And anybody have a different opinion?
I would say I don't know because I don't know the value of X or where is this?
I think what
Saturated mixture.
Okay,
Probably maybe.
if you don't know, then
Water state,
somebody
right?
who knows, please answer.
Water state. No.
Water state. What water? Well, steam is also water.
Yeah,
With
but
saturated steam.
Mixture.
Sorry?
Mixture.
Mixture. No,
Yes.
sorry, it's not mixture.
Saturated.
Saturated,
What state?
saturated steam.
Saturated water.
Saturated water. Okay. It is, let's have a look. This is water. This is steam. The difference between the two of them is that this is liquid, water is liquid, steam is vapor. So what is the reference state? This is liquid. That's liquid. That's vapor.
Liquid state.
Liquid state. Why?
Because the zero is under the liquid state.
Okay. Because you have this 0 here. Oh, what happened here? This was from the previous one. Oh dear. Let me see. Let me delete this. Don't know what happened. Why is this over here? Why is all this thing over here? Okay, let's say. Okay, that's good. We have this. Can you have a look from the previous slide? The reference is 0, right? The reference is 0. So have a look at your enthalpy. Your reference is 0. That is under liquid water. So your phase should be liquid water. You have to specify liquid. It's not steam. steam is vapor. So whenever you state your reference state, you have to write liquid water if you are using the steam table. Another thing, there's a zero here. That's for internal energy. This is for enthalpy. So you need to specify. How do you know what is your reference state? When the value is zero for your enthalpy, then that is your reference state, which is at this temperature, at this pressure. So at that temperature and that pressure is known as triple point. This is your triple point. It's very difficult for me to write using the point. Oh dear, this is getting ridiculous. Triple point. I'm not used to having a mouse as my pencil. So that's your triple point. That's a triple point. In a steam table, that is always your reference state. So whenever you use the steam table, you need to state your reference, which is the triple point. Any question? Any question?
Okay.
No? Good.
No.
Okay. We have looked at this example, 7 to 1, yesterday. I'm not sure. Okay. Any question on that? Nobody asked that question yesterday, so I'm going to look at example 7.2. Okay, 7.2, that is about, you have crude oil. Have a look at it. Those who have, if you have your textbook, you can read it from your textbook. You have, let me jot down first. I'm going to jot down using my handphone so that we can look at it later on. I have, in this example 7 to 2, you have mass flow rate 15 kilogram per second. Your mass is coming in at a different level. Let's draw our, I will show you guys my handphone later on, but right now I'm looking at my PowerPoint. (200 meters) coming in at 115. Below, that's ground. This is 220 meters. Below surface. My exit is 20 meters above the ground level. Calculate the potential energy. Calculate the increase in potential energy. Hold on, guys. Let me tidy up my. Okay. Let's stop this PowerPoint and have a look at my handphone. Okay, this is the example. I drew it. You have the feed coming in at 220 meters below surface, and your outlet is 20 meters above the surface. The equation asks for the change in the kinetic. Sorry, I got K there. It should be an energy change in the potential energy. Okay, change in potential energy. The equation for potential energy is equals to m, your mass, g is your gravitational acceleration, z is the height. So we need to specify a height. Let's say this is below. If it's at surface, this is surface. If it's at surface, z equal to 0. If it's above, this is above 20 meters, 20 meters above. Let me redo that. Yeah. That's 20 meters above. So from here to there, that's 20 meters. And from here, that's 220 meters. Okay, below. So we will have, when it's on the surface, the height is equal to 0. So now what's your mass? Your mass is equal to 15 oops, 15 kilogram per second. Okay, that's your mass. This we are calculating the difference. You need to have the value for gravitational acceleration 9.81. The unit is meter per second square. Again, you have the difference in the height z minus z. Every time you have a difference, the z should be final value minus initial value. Or another way of putting it is, normally we have a subscript of 2 for the outlet, 1 for the inlet. That's another way of putting it. So you can write final, you can write initial, or you can write outlet, or you can write in inlet. Either way, or 1 or 2. Let's just go down here. Okay. Your delta z can be written as z2 minus z1. Can also be written as z final minus z initial. Can also be written as z outlet out minus z in. It's up to you, whichever you want to use. Okay, but I stick with 2 or 1 either way, as long as you understand. Okay, so now your final outlet is 20 meter above the ground. Is above, so you give it z equals to positive 20. Above is above. Okay, if it's below, then that value will be minus 20 because your surface level is 0. So this will be z2, that will be z1, your height. Okay, so now let's put that value inside here. I need to undo that. Undo here. You will notice that we need to change the unit because energy has a unit of joules. There's no joule symbol here. There's no unit of joules here, so we need to convert later on to joules. So that's the Z2 just now is positive 20 minus 220. And the whole thing is in meter. Yeah. Below is negative. So if you calculate that, what will you get? Somebody. What will you get? I need to cancel the unit later on. If I look at the textbook, the answer is 35.3. Is it 35.3 or is it 35,000? 35,300. Somebody calculate?
30,280.
Sorry?
35,280.
280, is it? 280 or 208?
80.
80. Okay. Now the unit. We have a problem with the unit. The unit is kilogram. I'm repeating what I have written at the from the top equation. Sorry, I don't need to.
35,
35,000?
35,360.
260.
316.
360. 360.
35,316. 35316, ma'am.
Give me one value. Give me one
35316.
35316. 35316. Is it? Okay. You can check again with your calculation. Now I'm looking at the unit, second square, and we have meter. Okay, you have 2 meter, you have second square and second. Okay, now you need to get it into joules. Let's look at your conversion table, the one that is in my first slide, the conversion table. How do you get from the unit that we have now into the joules, into joules? We need to convert it to joules. Let me have a look at my textbook. Those who have your textbook, have a look at the front page. Just immediately after the front cover. How to convert? 1 joules or 1
1 joule is kilogram. meter square per second square.
1 joules per second. Is it? No.
Per second, yes, yes.
Joules per second.
Yes, ma'am.
Okay. Is equals to
kg
kg.
m square
M square. Second square.
second square minus like inverse square.
Yeah. Okay.
Yes.
That's it. Is that it? Is that it?
Yes.
Yeah.
Yes, that's 1 joule.
That's 1 joules. Okay. We cancel the kilogram. We cancel the M square. Now we cancel this. How come we got one extra S second, 1 extra unit per second?
That's it.
Also add one more
Will,
second.
1 joule per second.
1 joules per second? It should be 1 joule per second or 1 joules only?
1 joule
Joule per second.
Sorry?
Second per second.
1 joule.
Is it second there?
joule
Is
only.
there a second there?
No.
Oh, sorry, ma'am. The second S is removed.
Okay, is that it?
Yes, yes, ma'am.
Okay. So now our unit should be, let me rewrite. The unit is going to be 3,000. Anybody want to comment?
Doctor, I think it's kilojoules, not joules.
Kilojoules.
Yeah.
Have you looked at the, sorry, have a look at have a look at the conversion table at the
If
front page.
kilojoules will be 35 kilojoules.
Yeah, we
You want the
divide by
answer?
10.
The one that you have is 35,000 kilojoules, is it?
Yeah, 1 kilojoule per kilogram equals to meter cubic per second cubic.
Ah, right. This is the conversion factor, isn't it?
Yeah, but here it's joules, not kilojoules.
I did not write kilo.
Yeah.
It's joules. Only 1 joules. One. That's 1. Yeah, that's 1. So now we have joules per second, right? Once we cancel the rest of the units, we are left with that unit. So if you convert that into watts, that's going to be watts.
The same. The
Yeah.
same.
Same. So this is going to be your potential different in the potential energy. So let's look at the solution from the textbook. The solution from the textbook is slightly different. It's 35,300 watts. We managed to get 35,316. Well, I most probably the textbook round it off, but I think that's quite a big round off. Any questions on this problem? Anybody? It's just a calculation of potential energy. You need to know what is your, where is your reference state when z is equal to 0. And when you do this problem, please specify your basis. I forgot about that. Your basis is going to be that 15 kilogram per second. Of whatever substance is this, crude oil. You need to specify your basis. So, any questions?
No, that,
Good. So that's easy because that is just a simple calculation of potential energy. So let me unshare this and we continue with our PowerPoint. Okay. Where is my PowerPoint? Okay. We have done that. So now let's proceed to the next slide. Yeah, this is another example from your textbook. Example 741. Let's look at this question first before we handle the example. You have specific internal energy, that's U, the temperature, the pressure, that's the value. So I'm going to write it in, using my handphone. You guys have a look at the slide. You can also use your textbook to have a look at the problem. The specific internal energy is equal to 3,800. The unit is joules per mole. Your temperature is 300 Kelvin. The pressure is 1 atm. Okay, the specific molar volume at that same temperature, specific molar volume, that means is per unit mole. What is it? 24.63 liter per mole. What is required? The specific enthalpy. You need to find the specific enthalpy of this helium when you have a molar flow rate of 250 kilomole per hour. Okay. You need to have a specific enthalpy. Is it? Calculate the specific enthalpy and the rate of enthalpy. Specific enthalpy and the rate of the enthalpy. Or rate of enthalpy. So that's joules. Have a look at the unit. The unit is joules per mole. This is the rate. So you need to get your answer in joules per mole and joules per hour. Okay, so specific, and then we have the rate. Okay, okay, we need to, I have over here the gas constant. Why we need a gas constant? That's, we're going to use the gas constant as a conversion factor. So if you remember how we calculate just now, we will have conversion factor. So we will use this gas constant as our conversion factor. So let me go to my handphone first so that we can do this problem. Okay, what do we have? We have the specific enthalpy, internal energy. We have pressure, temperature, volume. What is required? The enthalpy. The enthalpy can be calculated according to this equation. Oh, sorry, I made a mistake there. That's right, isn't it? Enthalpy is equal to U plus PV, isn't it? Did I get that right? Anybody? Is that right? Have a look at your notes.
P delta V.
P delta V.
Oh, okay. Sama-sama.
Okay,
It's
that's
right.
inside your note, isn't it? Okay. You have your U 3800. I'm going to write down the unit. The unit is joules per mole. Okay. Plus, now, we're going to need P. Your P is 1 atm. Your V, 24.63. Oops. Oops. I thought I already, no notification, still coming per mole. Okay, have a look at the both sides. This unit is in joules per mole. That unit has nothing to do with joules per mole. But as far as you guys know, enthalpy is an energy. I mean, it's in joules. So you need to change the unit of your this whole thing into joules per mole. Then you can add it up. If you don't have both in the same, having the same unit, you cannot add it up. Okay, so now what we're going to do, we're going to change that into this joules per mole. 1 atm times by 24.63 liter per mole. Okay. Have a look at your gas constant. The one that I show, I'm not sure whether you can see the gas constant now on the screen. Can you see it? No. Guys, can you see?
Cannot see, Doctor.
Can see?
I can see that.
No, doctor.
You can see. Okay, let's go back to our PowerPoint then. Stop sharing this. Okay, let's share the PowerPoint. Okay, now you have the PowerPoint. Look at the unit that you just wrote just now for PV. What do you have? ATM, liter, and mole, isn't it? You have ATM. Oh, sorry. Hold on. I need to get my pencil. Okay. You have your liter, your ATM. You have your ATM. Oh, why I'm not getting anything? That's ATM. That's ATM. Where else? ATM. Okay. You have your pressure in ATM. That's what we multiply, the pressure. And we multiply with volume. Our volume is in liter per mole. Where is liter? That's liter. Oops. That's liter. Anywhere else liter? With this one, you have liter, but you don't have ATM there. Okay, that's the only thing that have liter. Okay, so you're going to use that as one of the value, and you need to have joules because your enthalpy should be in joules. So where do you have joules? This is joules. So once you have joules, so that's the unit you're going to do. You're going to use both these two values as your conversion factors. And so you know where to put the value because depending on the unit, you know it should cancel off. So you know what to do. Okay, let me jot down first the gas constant. Our gas constant is 8.314. I don't need to write too many decimal places per Kelvin per mole. There's another value that we're going to use, which is 0.8206 and liter ATM per Kelvin per mole. Okay, let's unshare this so that we can continue with our calculation with our example. I need to go to my phone. This will take some time. Yeah, I already wrote down. Oh, okay. I already wrote that value there. And that's the two gas constants that we just got just now. We're going to use it. So now, let's look at the equation that we have over here. You have your ATM there. That's your ATM. Yeah. So that means you're going in order to cancel it off, you need to put it over here in the decimal. I mean in the denominator, in order to cancel it off. So if you look at your gas constant just now, this is your ATM. So it's going to be 0.08206. I don't have enough space. Let me undo this first. Yeah. 0.0, what value is it just now? 8206. 8206. ATM. Let's have a look at the unit. Liter, mole, Kelvin. Okay, we cancel off ATM. We cancel the liter, but still there's no juice inside it. There's no juice written. So now we're going to use this is part of the gas constant in order to get juice. You know you have to cancel the Kelvin and the mole at the top here. So this will be mole. It will be Kelvin. And if you look at that unit, 8.314. 8.314 joules. So you cancel that off, cancel your Kelvin, you end up with a unit of joules per mole, which is the same as that unit. The same as that unit. Okay, so do the calculation. Somebody give me the answer. 24.63 times 8.314 divided by 0.08206. What's the answer, please? If I look at the textbook, where is the text? Where is this problem? This is 741. Okay. What's the answer, please? Somebody do the calculation for me.
2495.42.
2.495 times 10 to the power of 2. Anybody get a different value from that value? And everybody get the same value?
I got the same.
Yes.
Yes, ma'am. Sir.
Okay. So now that's the value for PV. Okay, so you're going to substitute it over there. I'm going to substitute it over here. So I'm going to 3800 plus, if you multiply this, is 249, isn't it? 0.5. 249.5. The same unit. So what's the answer? The answer from the textbook is, oh, did we make a mistake somewhere? How come we got this different value from the textbook? We did
Decimal
some
point,
calculation.
teacher.
Sorry?
Decimal point of the gas constant.
Decimal point. This is 2.495, isn't it?
Yes.
Because the textbook managed to get,
Sorry, ma'am, it's I think
it's not
Power
right.
3.
Sorry? Power 3.
Yeah, I got 2,495.
Okay, power 3. That's 2,495. Let me erase that. Okay, 2,000. 2,495. Okay, let's put that here. $2,495. So your answer will be, is it 6295? Hold on, guys. I need to a tissue.
Yes, ma'am. 6295.
6295.
Yes.
6295. So the unit is joules per mole. So that's the final answer of your specific enthalpy. It's quite messy, it's crowded, everything is there. That's the answer of your specific enthalpy. Any question on how to get that value? We're just using this equation. The part that is a bit tricky is to get that into joules per mole. And how do you do that? You are using the gas constant, these two values, so that you have the joules per mole. You cancel it off here, just like what we did here. So the answer is 6,295 joules per mole. Any questions? How to remember? Okay, I have a method how to remember. Remember, this is PV. You remember ideal gas law. What is ideal gas law?
PV is equal to nRT.
Okay, ideal gas law. PV equals to nRT. So every time you have PV, you'll be using your gas constant as the conversion unit, conversion factor, sorry. So every time you have PV, if you want to get it into the unit of joules or energy, you need to use your gas constant as the conversion factor. That's how you remember. Okay? But in fact, we are looking at helium, and the temperature and the pressure is valid for you to use ideal gas law. The temperature is high, not low. The pressure is not too high. So this we can assume ideal gas law. You can assume ideal gas law. Okay, the second part of the question, you need to get this, the rate of the enthalpy. The rate of the enthalpy is normally joules per unit time. The textbook asks for hour, joules per hour. So now that you already managed to get the specific enthalpy, we managed to get just now the specific enthalpy. We got 6,295 joules per mole. You know, you're not going to have mole over there because your unit for sorry, I got it wrong. I got this written wrong. This is supposed to be a dot. You need a rate. So let's undo that. Let me undo that. I need to write the unit so that everybody can see what's going on. Joules per hour. What you have is 6,295 joules per mole. You know you need to cancel the mole. And you need to have hour there. So how are you going to go about that? What do they have?
Multiplied by the molar flow rate.
Yeah. Where is the molar flow rate? There's the molar flow rate. There's the molar flow rate, which is 250 kilomole per hour. Multiply it with 250 kilomole per hour. Okay, you get hour there, but you cannot cancel the mole with the kilomole. So what do we have to do? Need to cancel this 1 kilomole. 1 kilomole is equal to
We converted 1,000 mole.
1,000, right. Your voice remind me of Muaz. I have a student by the name of Muaz. Your voice is exactly like his voice.
Me?
Uh-huh.
I don't know.
Maybe you don't, do you know Muaz?
No.
No.
Muaz.
Muaz. Muaz.
Muaz al-Hut. Yeah, I know him.
Yeah.
Yeah.
I thought you sound similar to his, your voice is the same.
I don't
Okay.
think so.
Okay, now everything is there. Cancel it off. Now you managed to get joules per hour, and the answer, if we look at the textbook, the answer is 1.57 times 10 to the power of 9 joules per hour. So that's the rate, enthalpy rate. Every time you have an equation, you look at the unit. You got to imagine how you're going to arrive to that unit and what is available. Okay, any questions? Any question?
No, no.
Clear.
Okay, clear, good. Okay, let's go back to our text, our PowerPoint. Stop sharing.
Doctor,
Yes.
the basis, we have to write 250 kilometer per hour, right?
No, sorry. Yes, 250. Sorry, I forgot that. I forgot about that just now. Yes, you need to write your basis. Yes, you do have to write your basis. You have to write your basis 250 kilomoles per hour. Your basis, yes. You don't have a reference state yet because you're calculating your enthalpy.
Thank you.
Welcome. Thank you for reminding us about the basis. I forgot completely about the basis. Okay, let's go back to our PowerPoint. Well, we've done that. Let's look at closed system. Closed system. We mentioned about closed system yesterday. It's completely closed. Nothing can enter it. Nothing can goes out from it. Okay, this is why I asked you about the textbook just now. Have a look. There's a different in equation. If you're using the old version, which is the 3rd edition, there's a negative sign there. Let me get my point. Okay, something to write. There's a negative sign there. But if you're using the latest edition, which is the 4th edition, there's a positive sign. So you need to know, you know, if you're using the negative sign, you might end up with a different answer. Not the value is the same, but the sign might be different. So I would suggest, if you're using the third the ebook from the internet, this version is available in the internet, the 3rd edition. Just remember that we're going to use this equation that is from the 4th edition. It should be positive. Do not stick with the negative. So if you're using the ebook or you have the old version, please correct it to the change it from negative to positive. Yeah, please take note of that because we're going to use the 4th edition. And so we're not going to use this equation at all. We're not going to stick with we're not going to use the 3rd edition. We just use the 4th edition. And now let's have a look at the equation. It's a closed system. If you have a closed system, you have delta internal energy. This one is kinetic energy. This one is potential energy. That's heat. That's work. Okay. So remember, everything that goes in, if you have this is your system. Oops. If this is your system, anything that goes in, if it's Q going in, then that will be positive. If if work is coming in, then work will be positive. If anything that goes out, negative. Easy enough to remember. Very easy. So if you're using the 3rd textbook, that is different. This thing is different. This is by. That means something is done by the system. This is something is done on the system. It's completely different. So stick with only one version, which is the 4th edition. We don't want you to get confused. So just stick with this positive sign there. Okay? So let's go to the next slide. Remember the delta signifies a change of this value. Okay, this is a closed system. When you don't have any acceleration, let me use my pencil again. Okay, no acceleration. Whoosh. No acceleration. Why am I not getting anything? Okay, no acceleration, kinetic energy is 0. That means there's no change in velocity. No change in height potential energy is 0. When the temperature of the surrounding area and the temperature of your system is the same, or your system is well insulated, that means it is adiabatic, Q is equals to 0. When there's no moving parts, no current flowing, no radiation, W work is 0. No temperature change, no phase change. That is what is normally being stated. Then your internal energy is equal to 0. Right? So internal energy is normally in terms of temperature. It changes due to temperature change. It is almost independent of pressure. It doesn't change much due to pressure unless there's a very big pressure difference. Then internal energy will change. Or else most of it is due to temperature change. So that's why you have, when there's no temperature change, internal energy is 0. Right? So sometimes it's specified in the question, assume that kinetic energy is negligible, potential energy is negligible. So when it's assumed kinetic energy is 0, potential energy is 0, you cancel that off, you end up with only internal energy is equals to heat plus work. That's easy. I'm just going to see whether we have an example on this. Okay, this is one example. 731. Let's use our, let me write down using my handphone first. Okay, guys, what's the time? Anybody? It's 2:58. Almost 3. Okay, guys, let's have a break. Come back at 3:05. Okay, guys, anybody like to ease yourself, stretch yourself? At 3:05, we'll start again to look at this example 731. For those who want to ask anything, you can ask. Or if you don't have anything to ask, okay, let's keep quiet for at least 7 minutes. Yeah.
Benda tu.
Yang berani tadi lah.
Oh,
Kumpul tu.
Bapak desperate ML. Asal? Diorang buat viewers dengan share lagi banyak lagi dapat banyak hadiah.
Viewers dengan like share.
Bukan. Nanti ayah tunggu aku tunjuk.
Sedih tu ML. Dia mesti dah menggeletar tu Arif nak keluar lepas Wolves. Tak lama dah dia nak kaya.
Ai.
meriam kan.
Ni minit nak up lah.
Minit lagi.
Oops.
Minit dah.
Jam.
Okay, guys, come back. Welcome back. I hope you guys managed to get some break from this lecture, and that will refresh you guys. Okay, let me try to. What happened here?
Boleh
Where
lah.
is my pointer? Okay, have a look at this example. Over here, can you hear me, guys?
Yeah.
Yeah.
Yes, doctor.
Over here, you have a gas inside a cylinder. The gas is fitted, the cylinder is fitted with a piston that can move. The temperature initially is at 25 degrees C. Inside that cylinder, you have boiling water. You put in 2 kilocalorie of heat into the cylinder. I mean, you heat it up, and that will increase the temperature from 25 to 100 degrees C. So the question is, solve for the energy balance. Now I need to hold on. I cannot move. My something is going. I can't seems to be getting anything. Okay, hold on. Hold on. Let me play from that slide. Current slide. Okay. Oh dear. Okay, guys, that's better. Okay, let's jot down what we have. We have a temperature of initially at 25. Initially, it was at 25. Oh, it was. Why am I not getting anything? At 25, you put in heat into the system. Now the temperature increased to 100 degrees C. So if we go back to our handphone, before that, let's look at the second stage. Once you have got it at 100 degrees C, the gas now is heated up. So the gas is heated up at 100, and you release the piston. So what happened? The piston will move up from its initial position, and the piston will move up. Most of you have come across this example, this sort of problem, in thermodynamic. So now there is a bigger volume, but still the temperature is the same. There's no change in temperature. The temperature is still the same. It's just that there is work being done by the gas. So the work that is being done by the gas is 100. The gas does work, which is 100 joules. Right? That means the gas is releasing work. Q is equal to getting out. Here, over here, you have heat in. Heat in, so that means heat is going into the system. That's Q is going into the system. So you need to know the symbol. So what for the first case? For the first case, heat is coming in. So what symbol are we going to use? Positive or negative, guys?
Positive.
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 How about for the second stage, where the work is being released by the gas? That means it's coming out of the
Negative.
system.
Negative.
Good. So you need,
Negative.
good. So you need to know that it's very easy to remember. Just anything that goes in positive. Okay, let's unshare this and look at our. Let me scribble using my handphone. Okay. Okay, now I have the first case. Just now you mentioned that in is positive, so this is positive. Let me write. I'm not going to write the positive sign because it's understood. For the second case, it is negative because Q is getting out, so that's negative. And let's write the system is a closed system. If you want to write a basis, you can say what basis. What is there any amount here? No amount, isn't it? No amount. There's no amount of the gas. So I guess don't need to write the basis then. Or you can no, nothing to write the basis. So we don't need to write the basis because there's no amount. Okay. We have initial temperature. Now this is a closed system. The equation is delta U plus the kinetic energy plus the potential energy equals to heat plus W. Okay? The problem states that you can ignore the potential energy due to the movement of the piston. You can ignore that at the very last part of the question. The system itself is not moving. The system is stationary. So your kinetic energy is also zero. That's zero. So you end up with just the internal energy, the heat plus work. Okay? So what do we have for the first case? For the first case, heat is coming in. That's Q. You don't have any work. Nothing is moving. For the first case, nothing is moving. Your gas is inside there, still trapped. Nothing is moving. So work is zero. Okay? So you know that Q is equals to 2 kilocalorie. 2 kilocalorie, but normally if you use a SI unit, you don't deal with kilocalorie. So now you need to change it from calorie into joules. So have a look at inside your textbook at the conversion table on page behind the front cover on the first page, which is we are looking at kilocalorie. Do we have kilocalorie here? We have calorie.
Only calorie.
Only calorie. Okay. So change this into the calorie then. Times 10 to the power of 3.
Doctor,
Yes.
in fourth edition there is 0.23901 times 10 to the power minus 3 kilocalorie.
Oh, okay. Okay, good. I'm looking at the third edition, so it doesn't matter. We already changed it into calorie, so it doesn't matter. It's still the same. Okay?
Okay.
But if you have that fourth edition, stay with use the fourth edition. Use the kilocalorie. You will end up with the same answer. Okay, so let's me use the conversion table. What is the calorie that I have? Calorie 0.23901 calorie is equivalent to 1 joule. Okay. Calorie. So cancel the calorie. So your answer will be in joules. Let's see the solution from the textbook. What is the answer in joules? The answer from the textbook is 8,000 370. What's the value that you guys managed to get if you do the calculation?
8367.9.
Okay, slight different because of rounding off. 8367.9 joules. If you calculate it, that's the answer. The textbook somehow just round it off. Yeah. So that is your delta U for the first case. Again, let's look at the equation. You don't have any kinetic energy. Why? Because your system is fixed. It's not moving. You don't have any potential energy because the system is not rising. Neither is it, going down or going up. The system is fixed, stationary also. So you don't have any work. The work is zero because your system is not. There's nothing moving in it. There's no moving parts. There's no turbine. Nothing moving. So work is equal to zero. Any question on this? The first case? Anybody? Nobody? No question? Okay, let's look at the second case. After you have managed to reach 100 degrees C, you release the piston. So what happened? The piston now moved from its initial position. It moved outwards, and in doing because the work that is given out from this there's work getting out of, but the gas is moving the piston. So when the gas is moving the piston, that means the gas is doing work. So the amount of work is 100 joules. So just now we mentioned that if work is going out, it should be negative. Right? So let's again rewrite the equation for a closed system. We have delta U, delta E kinetic, delta E potential equals to Q heat plus work. Again, inside our text, the problem is stated that you can assume that because the piston move, you can, even though the piston move, you can assume that there's no potential energy. Okay? It's stated in the question. And obviously, the cylinder doesn't move. There's no kinetic energy. Now, do you have any heat coming out for the second case? Any heat being put in, any heat being taken out?
No.
No, so that's zero. So you end up with delta U equals to W. Oops. I got it wrong. Sorry guys. Even though there should be heat. Why is there heat? Because something is moving. Something is moving. There should be heat. What? It should be delta U equals to zero. Why is delta U zero? Remember I said when there's no change in temperature,
Adiabatic.
when there's no change in temperature, that means delta U is equal to zero. When there's no change in temperature, your temperature is still the same, 100. Both of them are at 100 degrees C. So delta U is equal to zero. So now delta U, not Q. Q, there is heat. Why? Because when the piston moves, there has to be a heat. So now you end up with this equation, Q plus W equals to zero. Yeah. So since you know what is W? W is minus 100. So Q plus minus 100 equals to zero. And that means heat is equal to 100 joules. Just now, this is in joules. That's joules, okay? So that's 100 joules. So that's your final answer. Q is positive. Why is Q positive? Let's look. That means heat is coming in. Heat is coming in. The heat is coming in. The heat is coming in, but why is the temperature still at 100 degrees C? Anybody?
Because there is a work. The
Yeah.
piston has moved.
Because the amount of heat that is there, the gas got heated up, so it pushed the piston up. So even though it is the heat is being put in, the temperature still maintained at 100 degrees C because the piston is the one that is moving. So the heat now changed to work. So So that's why the system is still at 100 degrees C. That's the final answer. So any questions? You guys know this part because this is in thermodynamic. It's very, 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 you guys have done it in thermodynamic, so you should be very familiar with this kind of problem. This is just to recap the use of symbols, positive, negative. Even though you are using the old textbook, which is the 3rd edition, the answer is still the same, 100 joules. You still come up to the same answer, but you just need to maintain the symbol that you're using. But I would suggest, please do not stick with this equation, which is positive for the closed system. You need to have this symbol positive. Need to have the symbol positive. Any questions, guys?
No, doctor.
No. Okay, I will stop this and we'll continue with our PowerPoint. It's a bit awkward, isn't it? Teaching like this online, keep on changing. But we have to make do with what we have. The situation is not, is very, very, the pandemic is still going on, so what to do? Okay, now let's look at open system. Open system, the mass is coming in, the energy is coming in, the mass is going out, energy is going out. So the difference between the previous closed system and open system is in terms of the equation. I mentioned this before. The equation is the enthalpy. You don't have delta U, you don't have delta H. Okay. If you have a closed system, this will be delta U. But if you have an open system, it's delta H. So that's the difference. Okay. Why is there a dot? I did mention yesterday, somebody asked. The dot means rate. That's rate. So there should be a dot here also. There should be a dot there also. In terms of the mass. Or else you cannot have a dot over here. Okay. So the difference in enthalpy is out minus in. Okay. Or final minus initial. So that's mass flow rate by specific enthalpy. Because your unit for enthalpy over here will be joules. For example, the previous example we have per hour. Right. So over here, your enthalpy over here will be joules per kilogram. Oh dear. Very, very difficult trying to write with a mouse. That's per kilogram. And this mass is normally kilogram per hour. I'm struggling here with this mouse. Oh dear. I'm writing just like a small kid. Okay. So that's how you get joules per hour. Yeah. Now, there's another thing. Symbol subscript S. Your work, previously when you were looking at closed system, there's no subscript. Now, there is a subscript S. That stands for shaft work. Shaft work, that means there will be moving parts inside your system. You have a turbine, you have maybe a shaft, you have a propeller moving inside the system. So that's shaft work. Okay. Inside your textbook, if you look at inside your textbook, there's a derivation of that equation. It's a very long derivation. In fact, it's one whole page of it. The topic is 7.4. The steady state open system energy balance. 7.4C. That's the topic. I'm not sure inside the new textbook, is it still the same? 7.4C. Is it? 7.4C. Anybody? Anybody? You don't have your textbook with you?
Yes,
Okay, good. It's 7.4C. So how to derive it? Have a look, because I'm not going to go through it. I'm just going to get the final equation, which is that equation that over here. We're not going to look at the derivation because you're not going to be asked how to derive. Obviously not. If you are being asked how to derive, you just copy from the textbook. There is an open textbook test, so I don't think now anybody is going to ask you to derive. So this is the final equation. So let's see whether we have any problem. All right, we have an example here. Now, over here you have the flow rate. Oops. No. I'm not going to start my video. I'm going to start my video. I'm going to do. Right. Okay. You have 500 kilogram. That's your basis. You have steam. It's entering at 44 atm. I'm not sure whether I have the diagram here. Oh, I don't have the diagram. Is there a diagram with this? No, there's no diagram. Okay. You have your steam coming in at 44 and the temperature is 450. Oh dear, sorry guys. I seem to be messing up. I wanted to use the pen in order to highlight. That's 500, 44 atm. Your temperature 450, 60 meter per second. The entrance is 5 meter below. Below, you take note of that. Below, no, that's lift. The entrance is not mentioned at what point, but this is below the inlet. That's the velocity. The shaft work. The shaft work is 70. Your heat loss. There's heat loss. That's 4 times 10 to the power 4. Specific enthalpy is what you need to find. Okay, let's jot down what we have. Let me write in my handphone. I have. Let me draw first. Okay, I have 500 coming in, 500 kilogram per hour. Let's share the okay, unshare this and share my handphone. How are you guys coping with this online system right now with my lecture? Are you guys okay with it? Anybody want to
So far, so
respond?
good, ma'am.
Okay, good. Okay, we have, let's continue. We have 500 kilogram. This is example. Oops, sorry. Sorry. Somebody just left. Is it? Okay, we have 500 kilogram of steam. You are entering it at, okay, that's the entrance. And you are going to exit somewhere 5 meter below. The condition of entrance is 444 atm and 450 for temperature. Your velocity 60 meter per second. Okay, that's done. For the exit, you still have 500 kilogram per second of steam because nothing is, it's just input and output. In the velocity below inlet at atmospheric pressure, P is equal to 1 atm. Temperature, no change in temperature, I guess. There's no mention of it. U is equal to 360 meter per second. Okay, right now you have deliver shaft work. The turbine deliver shaft work. Deliver, WS. What do you think will be the sign? Will it be positive? Will it be negative? Deliver. What do you mean by deliver?
Negative.
Positive.
Positive, like produce.
Okay, the turbine is producing energy.
Yes.
So that means Q is going to be getting out, isn't it? From the system. So it should be negative. Is that correct? It deliver. Q is going to be negative. And what else do we know? We know heat loss. Is Q positive or negative, guys?
Negative.
Negative.
It lost negative.
Okay. Need to confirm it. Now, Q heat loss. Heat loss means it's getting out of the system. Q. So what is that? Positive or negative?
So
Negative 10
Negative, thank you. Negative 10 to the power 4.
kilocal per hour.
Yes, kilo. And if you guys are using the new textbook, you can easily change it to joules, kilowatt. I'm sorry. That is per hour. Yeah. Let's look at our system now. We have an open system coming in and out, so it's open. Before that, basis, guys, what is your basis?
500 kilograms.
500 kilogram per hour.
Oh my God, somebody is calling. Oh my God. 500 kilogram. That's the bad thing about using a handphone as a whiteboard. Okay. 500 kilogram per hour of steam coming in. That's your basis. In. Coming, fit. Ouch. Oh dear. Fit. Huh? 400 kilogram per hour of fit. So it's open system. Your system delta H plus delta E plus delta E potential equals to heat plus W. Let me erase that. Okay. Okay, we have flow rate. This is flow rate, kilogram per hour, so we will have rate. So we have the dot there. We have the dot there. Yeah, so the dot indicate the rate. Yeah. So that's the rate. So what do we have? We have everything here. You have everything here. You have work, you have heat, you have change in velocity. The inlet velocity, let's say this is in. Let's use a symbol of, okay, this is in. Just let in, this is out. Okay. This is in. That's out. That's out. In, that's in. Okay. Everything is there. You cannot cancel any of it. You have kinetic. Oh dear. Somebody is very persistent in trying to contact me. Okay. Your kinetic energy is there. Potential energy is there. Why is there potential energy? Because there's a difference in height. Okay. You have enthalpy there. Okay. Let's calculate the first thing first. The kinetic energy. First to half. Oh dear, my God, this person is really persistent. I'm having class. Wait, but the square now is a different. There's a different there. So this is minus. Yeah. So what minus what? Should be out minus in.
360 minus 60.
Yeah. So let me rewrite this in. So what do we have? We have the mass. Let me half. The mass is 500 kilogram. Let's change the kilogram per hour first. Don't write the 500 over here because we're going to use a lot of that mass in our problem. Okay, let's use, right, I don't have enough space. I'm going to write it somewhere very at the bottom. 500 kilogram per hour. I want to change it into per second. Equals to, wow, what is that?
0.1389.
0.1389 kilogram per second. Thank you.
0.1389.
13, okay, thank you. 0.1389, thank you. So that's our value, 0.1389. So need to remember that. 0.1389 kilogram per second. And now we have the difference in velocity. Our outlet velocity 360. Remember to put the square minus the inlet velocity 60. And your unit will change also. Meter square. I don't need to put that. Meter square, second square. Okay. So if you calculate that, what will you get? Somebody calculate it for me, please. What's the answer?
It .7507.
Okay, 750
.7.
7. Thank you. So the unit we have is kilogram second meter square. Oh God, this person is really persistent. Okay, you need to change your unit having the same unit as kilo. You have this kilowatt over here. We want it to be in kilowatt. So everything must be in kilowatt. So now you need to use your conversion factor. Remember, 1 joules is how many? What's the unit? Let's go back to our. You guys have your textbook, right? Okay, let me stop this first. Let me stop sharing first. Go to our PowerPoint. I want to show you guys the unit that we are going to have. The unit, oh, this is going forward. I'm going backward. Hold on. I need to go to the first slide. Okay, I just need to show this. Okay. The unit that we need in order to change to kilowatt. This is 1 joules or 1 watt. We need watt. This is watt. Oh dear, why I'm not getting my pencil? It's not working. Hold on, excuse me. This person is really persistent. I really need to answer this person. Hello, I'm in my class right now. Okay, 1 watt is equals to 1 joules per second. And you have 1 joules, 1 Newton meter. And how to get rid of Newton meter? 1 Newton is equals to 1 kilogram meter second square. Yeah. Guys, are you with me?
Yes, yes, yes.
Okay. Let's jot down the unit now, because I really need the unit, because I cannot go back and forth. 1 joules. I don't know why this person is so persistent in calling me up. I'm having class, and this person really wanted to call me up. I don't know why. Okay, 1 Newton is equals to 1 kilogram meter second square. Okay, let's go back to our problem. I need to share my handphone. This is going to, I think this is already 3:36. This is going to be our last example. Quite a long one. Okay. How to get it into kilowatt? Okay, what we have? We have kilogram. Change it to Newton. We have kilogram there. 1 kilogram meter second square is equals to, we're using this now, 1 Newton. You cancel that, you cancel that. Okay, you have your second square. Oops. You have your second square. Okay. Now, Newton. How to get your Newton? You have that equation. That's part of the conversion. 1 Newton meter equals to 1 joules. Cancel the Newton. You have meter square, meter square, that meter square cancels. Okay, you have 1 joules per second already. That is already 1 watt, isn't it?
Yes.
Okay, so what's the final answer? Joules per second. Sama. Okay, nothing changed, isn't it? 8750.7. Now, the unit that we are interested in actually is kilowatt. So change that into kilowatt. That will be 8.7507 kilowatt. That's your kinetic energy. Delta E. Okay. You do the same thing for potential energy. Delta EP is equal to mass, gravitational acceleration, and the change of the height. Out minus in. Okay, so your mass is going to be same value just now. What did we get just now? 0.138. 0.1389 kilogram per second. Your gravitational acceleration, this is the same value, meter second square. Now, your difference in height. The problem state that the inlet is here and below the outlet is 5 meter below. So if you specify that this inlet, when the z is equal to 0, the height is equal to 0, so this will be below, so that will be negative. So your z is -5 for the outlet. Because this you specify as 0, the inlet is coming in at when is z equal to 0, and this is minus below 5 meters, so there will be a minus sign there. Okay, there's a minus sign. So your outlet is -5 meter. Oops. -5 meter minus 0. Your inlet is 0. That's meter. Again, you need to convert it. So what's the answer first? Please, guys, what's the answer?
Doctor, it's 0.139 kilogram per second, not 1389.
Sorry? What the
It's 0.139, not 0.1389.
39.
The mole flow rate.
0.139.
Mass flow rate, sorry.
Oh, 0.139. No,
Yeah.
89.
No, 89.
Okay. I think that's close enough, isn't it? I don't think it will change much.
Yeah, it's close. I think if you round it.
Yeah. That will change this also, isn't it? The answer will not be that significant, isn't it? It will not be that significant. Yeah, if you want to correct it, it's up to you. Okay, now, what's the answer, please? Anybody? Give me a value, please.
-6.82.
Okay, let me erase that because I need space. Negative 0 point. What's the answer?
No, I got
-6.82.
6 point.
-6.82.
I believe 6.81.
Okay. So now we need to change the unit. We still have the unit that we need to handle with. Okay, meter second square, and then you have 100 meter. So now again we do the same. Where is that thing now that I wrote down? I have 1 joule. I wrote it somewhere here. Okay, there. 1 kilogram Newton meter. I need to change 1 kilogram meter second square. Okay, cancel the kilogram. Cancel 1 meter. Now I need to get into joules. So 1 Newton, 1 joules, 1 Newton meter. This is going to be 1 meter, isn't it? 1 Newton. Okay, so 1 Newton meter. One joules. Oh, no, sorry. I should not cancel that. Newton is the one. Meter is cancelled. What else? Second square, second square. So now the answer is still negative, the same value. Joules per second. Now I wanted it to be in kilojoules. This is watt. I wanted it to be kilowatt. So 6.82 times 10 to the power of watt in order to get kilowatt. Anybody? Anybody?
-3.
-3. Thank you. Yeah, so that's done. We have our potential, different in potential energy. We already have our kinetic energy. We already have our heat. there. Oh, we need to change that to kilowatt too. So that's easy. Negative 10 to the power 4. Kilocalorie. Give me the conversion factor, please. Anybody? Anybody? Do I have to look up my conversion factor myself?
0.239.
Okay, 0.23901 calorie per second. Okay, this is per second. Is equals to 1 watt. Okay, now, is there a calorie per second for the heat? The heat is kilocalorie per hour. Sorry, I forgot about the per hour. Yeah, there's an hour there. And now, change, we cannot cancel that. So I'm going to put the second up there. Okay. And 1 hour, 3,600 seconds. And there's another thing. This is kilo. That is 1 kilocalorie. So 10 power 3 calorie. Oops. I need to tidy up a bit. Calorie. So that's calorie cancel off, calorie cancel off, kilocalorie cancel off, hour cancel off. So it's second cancel off. That's what. So what's the answer? Minus. Anybody? It's almost 345. What's the answer? If I look at the textbook, let's see whether the textbook have the answer for the. Okay, the textbook, the answer is minus 11.6 kilowatt. Did you get the same answer? Guys?
Yes, yes, Doctor.
Yes.
Okay, now we have everything there. So now all we have to do is put down the values. We have our enthalpy, we have our kinetic energy, we have our potential energy, and we have Q, and then we have our work. Okay. So what kinetic energy just now we got 8 something. 8.7501. Okay, 8.7501. That's our kinetic energy. That's our kinetic energy. 8.7501. Seven, isn't it? Potential energy. I'm scrolling up. You guys got it written. You should help me with this so that we can
Negative 6.81.
negative 6.81.
81
Okay.
times 10 power of negative 3.
Okay. Next, the kinetic energy is equals to Q. The Q that we got just now, negative 11.6, and the work that is given in the problem itself. The work is negative 70. Shaft work. Oh dear, I forgot to write the shaft, the subscript. Remember the subscript. Okay. That's negative 70, isn't it?
Yes.
Okay. So now solve for your enthalpy. What's the answer? The same unit, everything is the same, so I'm not going to write the unit. All of them in kilowatt, so the unit will be in kilowatt. Let me rewrite that.
Negative 90.34
Okay, this is 7.
kilowatt.
Okay, that's negative 90.34
4
kilowatt. Okay, that's the answer. That's the question asked for calculate the specific enthalpy. This is not specific. Specific enthalpy is like this. That's specific. So remember just now, the unit for specific enthalpy is
Kilogram.
what? Joules per kilogram, isn't it? Specific.
Yes.
And the rate is joules per, for example, hour, right? For example, okay. So then you got to get it into in terms of kilogram. So let's look at our what we have. We need to get this value. We have delta H in terms of, if we write it in terms of kilojoules per second. So in order to get that joules per kilogram, what do we have to do? In order to get this unit is kilojoules per second is what? That's kilowatt.
Kilowatt. Divide by
divide by mole flow
divide
rate.
by the
Mass flow rate.
Mass flow rate. Mass
flow rate.
kilogram. If we have second, then we cancel that, isn't it?
Yeah.
Okay, now what is our mass flow rate? Just now, 0.139 kilogram per
100
second.
kilogram per hour.
No, we already converted it. We converted it. There. We said it was supposed to add 39, isn't it? We said it just now. Yeah, so kilogram per hour. So this is going to be 0.139 kilogram per second, and the value that we have for our interspecific and the rate that we have just now is minus 90.34 kilojoules per second. Cancel off the second, you will end up with that value. What is it in kilojoules per kilogram?
Negative 650.
650. Okay, that's the final answer. So you have two answers over here, the specific enthalpy and the rate of enthalpy change. Okay. In this example, it really uses the whole thing. This is the equation. Okay. I need to remember to write the equation with a subscript S. That's the subscript S, don't forget. Okay. Because the shaft is turning. That's the turbine is turning. So that's your final answers. You have, let me put it like that. Okay, now you have the two final answers. Any question? Guys?
No, Doctor.
Okay, that's good. So we are done. It's 3:50 now. So have a look at it if you don't understand what's going on, especially with this example. Have a look at it from your textbook. Try to understand it, and I think it's quite. Is the only thing that is challenging about it is changing the unit from whatever is given to the unit of kilowatts. That's the only thing that is quite challenging here. The rest is just straightforward calculation. Hey guys.